right, hey everybody. So you're in for a treat. Today I'm going to take you through the nuclear chem notes. We're going to do it slightly different. I'm going to throw myself in one of the corners of this video. I'm not quite sure where yet, and I'm going to give you a commentary of the notes as a voiceover, but you'll see me anyway. So it's kind of like a response video to my own response video. So we'll kind of see what I'm thinking as I'm going through this, and I'll explain these notes to you, and we'll go from there. So I'm watching these on the computer as you guys are, and we'll just kind of go from there. So see what happens, right? All right, here we go. Click and play. So we obviously start off with a black screen here. Definitely should have cut that out. Here we go. All right, so we are learning all about nuclear chemistry today. Underline it, must be important. The first thing that we really want to talk about are nuclear reactions, and we abbreviate reactions RXN. So anytime you see RXN, we're talking about reactions. Looking at unstable nuclei, they will undergo radioactive decay or nuclear reactions, and the whole purpose of them undergoing these reactions is to become more stable. See, atoms always want to be more stable. They will do anything to be more stable. They do not want to be unstable, if you didn't get that. So thinking about that, why would an atom be unstable? Well, think about where the majority of its mass is, in the nucleus, that small little inner circle there. Who lives outside the nucleus? It's the electrons. Who lives inside the nucleus? It's the protons, and it's also the neutrons. So think about those protons, those charges, right? They're pluses. And all these pluses, all these like charges, they want to just like repel away. Well, the neutrons in there, those act like the glue. My God, it's like I wrote this. It's crazy. Anyway, those act like the glue that hold the protons together. Well, sometimes there's not enough glue, okay? And those protons, the repulsive forces will push apart, and you eventually can get radioactive decay. You can get an atom that is unstable and will want to become stable. All right. So the atom will undergo radioactive decay. I don't know about you, but this is going pretty good. Now, don't get me wrong. I might make a mistake in the future, but we shall see. So let's see. So it'll undergo radioactive decay until it becomes stable. And in most cases, a stable nuclei is one that is lighter than the original one. So, oh, it made a mistake there. No, it should have been in an equation. So EQ is equation, the abbreviation for equation. So in an equation representing a nuclear reaction, there are two things you definitely want to always make sure of. You want to make sure that the sum of the atomic numbers, AN, the sum of the atomic numbers, and the sum of the mass numbers on either side of the equation, they have to equal each other. Meaning if your atomic numbers on the left side of the arrow, the left side of the equation equal 5, your atomic numbers on the right side of the arrow also have to equal 5. Same thing with the mass number. So let's take a look at an example down here. So in this example, it looks like we're doing beryllium, a mass number of 9, atomic number of 4. And we're going to be combining that with a helium atom, mass number of 4, atomic number of 2. When these two nuclei hit each other, they produce a carbon atom. And this new thing that we're looking at here, 1, 0, N. The most important thing here is to look at adding the mass numbers. 9 and 4, that's 13. Add the mass numbers on the other side, 12 and 1, that's 13. 13 and 13, we're good. With the atomic numbers, 4 and 2, that's 6. 6 and 0, that's also 6. So we are happy, happy, happy. Happy campers now. So what's the deal with that whole 1, 0, N that we just saw? Well, think about what that could represent. We're talking about subatomic particles now. We have protons, we have neutrons, and we have electrons. So with regard to a proton, it has a charge of, we'll say, a +1. And it has a mass of 1 AMU. So we're going to write this as 1, 1 P. Okay, so 1 on the top, 1 on the bottom, P. That 1 on the top is talking about the mass. The 1 on the bottom is talking about the charge. An electron. Charge is -1. The mass, it's relatively 0. So this one, following the same ruling, will have a 0 on top, a -1 on the bottom, and with a little e. Again, the bottom number is the electron, the top number is the mass. The bottom number is the charge, the top number is the mass. Now this one should look very familiar. This is the one we just saw, the neutron. Charge of 0, mass of 1. It is a 1 on top, a 0 on the bottom, and a little n for the neutron. So looking at that equation that we wrote previously, that 1, 0, n, at the end of the equation was a neutron. So what are these reactions called? They're called transmutations. And we notice that a transmutation has occurred. How do we know this? Well, a transmutation is a change in the identity of a nucleus, and it's due to a change in the atomic number. Now, please remember, if you change the atomic number, you are changing the atom. There's no ifs, ands, or buts about it. You are changing the atom. Remember, important. Come on, Mr. Fabs, what are you thinking here? You change the atomic number, change the protons, you change the atomic number, you change the atom. Very important. Let's see. So let's take a look at an example here. We have 212 polonium over 84. That is going to produce 4/2 helium and a question mark. So let's pause the video right there for a second. Let's think about this. Okay. I paused it for you. But let's think about this. Remember what we said. The atomic number on the top, on each side of the equation, they have to equal each other. The mass number on the top. Each side of the equation has to equal each other. The atomic number on the bottom, each side of the equation has to equal each other. So we have 212 on one side. We have 4 and question mark on the other. What number plus 4 will equal 212? If you said 208, you are correct. Take a look at the bottom. We have 84. What number plus 2 will equal 84? If you said 82, you're also correct. So what you want to do is you want to go to your periodic table. You want to look up what atomic number corresponds to 82. You'll get your answer. So let's see, we're writing down 208 on top. We said that. We said 82 on the bottom. We're looking at our periodic table, and it is Pb for lead. Let's try another example here. 253, 99, Einsteinium, 42 helium. All right. Whoa, this one's getting a little complicated. Let's pause this. Again, looking at the top, we have 253 and 4. Those are the mass numbers on one side. Those have to equal the mass numbers on the other side. So currently we have a 1 on the other side, so question mark. What number plus 1 will give us 257? If you said 256, you're right. Take a look at the bottom. 99 plus 2, that's going to give us 101. What number, now we have a 0 on the other side already, so what number plus 0 equals 101? I swear I am not trying to trick you. The answer is 101. Play this video, see what happens. 253 and 4, that's 257. So we're going to add 256 onto the other side. Ms. Fabs, you were lacking there, okay? 99 and 2 is 101. We got the molybdenum, or excuse me, mendelevium, I think. Try this next one on your own. 142 in PM, 61, plus something gives us 142 and 60 Nd. So we need that 0 on the top. We need the -1 for the electron on the bottom. So very important. That one was actually an electron. So if you just take a look at here, Mr. F, so what is happening in these reactions? Okay, question mark, question mark. Before we move on, I want you guys to take a look. The first example, that was a helium atom. The second example was a neutron. And the third example, we had an electron being injected here, okay? So what exactly is happening? Let's continue this and get on with The notes here, we are about halfway through, guys. So this is radioactive decay at its best. So there are some definitions that we need to talk about first. There are actually three of them. While I write this, I'm going to take a quick sip of juice here. A lot of talking. You guys must be bored listening to me. Hope everything's going well with you guys. Hope you're enjoying the video. Hope you're enjoying class. Hope you're enjoying nuclear chem. So back to these definitions. Radioactive nuclide, that is an unstable nucleus. Since it's unstable, it is going to have to undergo radioactive decay. Radioactive decay, well, that is the spontaneous disintegration of a nucleus into a slightly lighter, very important, a slightly lighter and more stable nucleus. It's usually accompanied by an emission of particles, protons, neutrons, electrons, and or the emission of electromagnetic radiation. Very important. It could be one, it could be both. And a nuclear radiation, that is particles or electromagnetic radiation that is emitted from a nucleus during decay. All right, Fabs, come on. You should have cut that out. I should have got that in post-editing. It should have been smoother. I know you're probably saying I should have went with a nice transition, but this is just like a quick and dirty notes video, so we're just going through this. All right, so I talked about radioactive decay. There are 3 different types of radioactive decay that we're going to familiarize ourselves with. So let's see, I got a table going on here. We got type, symbol, charge, mass in AMUs. AMU stands for atomic mass unit. Okay, so the first type of radioactive decay is the alpha particle. Now, there are 2 ways to write an alpha particle. You can either write it by writing 4/2 and then the alpha sign, or you can write it 4/2 in helium. They mean the exact same thing. And in case you just realized this, I will confirm it for you. An alpha particle is a helium atom. Yes, I kid you not, an alpha particle is a helium atom. All right, so let's continue on with this. Let's look at the charge. It is a 2+ charge, and the mass of this is 4.00260. And you could have probably guessed that it was going to be pretty close to 4 because look at the mass number and the symbols. It's 4. The next type of radioactive decay would be the beta particle, alpha, beta. There we're looking at 0/-1 beta, or 0/-1 electron. It is the exact same thing as electron. Oh my God! So we have helium is an alpha particle. We have an electron is a beta particle. Continuing on, we see the charge of this would be a -1 or a 1-, and the mass is roughly 0. Now, the next one, alpha, beta, and gamma. We have a gamma wait a minute. It's not a particle. It's radiation. It's a ray. It's a wave. Very important. So the symbol for this is just the gamma symbol. Now, I'm not very good at drawing gamma symbols, so I kind of go through a couple of these. Man, that was a bad one. That's not too bad. The charge on this would be 0, and the mass would be 0 because it is a ray. It's a wave. There's no particle. There's no mass. A little bit more, guys. I just want to explain to you a little bit more about alpha, beta, and gamma emissions or radiation. We're going to start off with alpha emissions, just a couple short little points on these. The alpha emissions, let's see. With regard to this, we're looking at 2 protons bonded to 2 neutrons. That's what an alpha emission or an alpha particle is. Continuing on, more about alpha emissions, we're looking at it's emitted from the nuclei of an unstable nucleus during decay. And these alpha emissions, they're not very strong. They don't have a lot of penetrating power. In fact, clothing or paper can stop alpha radiation. Now, when you get to beta emissions, they're slightly stronger, and you'll see that in just a second. A beta emission, if you remember, let's see, beta emission, that is an electron. Straight up, just an electron. And that is also emitted from a nucleus during radioactive decay. And this is about 100 times stronger than an alpha emission. So it can go through clothes. Okay, it can go through paper. And in fact, beta radiation is strong enough so that it can actually damage your skin. Okay, so 100 times more penetrating than alpha, and it could damage your skin. Now the last one, that is what changed the Hulk into the Hulk, or Bruce Banner into the Hulk. It is gamma emissions. And if you remember, this is not a particle at all. It is a high energy electromagnetic wave. Yes, it is a wave. Going a little bit further, let's see, this is emitted from the nucleus during decay. It is the strongest of all our radioactive decay. It does not consist of a particle. There is no mass. There's no particle. No mass. No charge, no particle. And it is the strongest. And in fact, it can only be stopped by lead. It is extremely dangerous. And as we saw, it turned Bruce Banner into the Hulk. I mean, you get hit with gamma radiation, it's not fun. Not fun at all. So that's pretty much the end of our notes. I want to just give you guys some examples, and I would really like if you guys went over these examples, answer them to the best of your ability. Here we're looking at 234 TH90. That's going to break down into 234 PA91 plus something. I'm going to give you guys a bunch of examples here. I want you to fill these in, and I also want you to tell me the type of radiation that's occurring. Is it alpha? Is it beta? Is it gamma? And that is probably where we will leave our notes for the day. So as it's going through, I really hope you guys enjoyed this type of note-taking. A little bit of commentary on the side. Remember that your alpha, your beta radiation, those are particles. Your alpha, right there, there's beta radiation. Number 3, beta radiation. So remember those are the particles, alpha and beta. That's what you're going to be writing down here. You'll be given it, but please identify it. Goodness, I think that is about it for this notes video. So everybody, have a wonderful day. Please be safe out there. Enjoy yourself. We're going into a weekend, so have a wonderful weekend. And I will see you guys in the next video, notes video, mug collection video, update video. I don't know what's next. I'm still trying to figure out this whole channel. And that is it, guys. So I apologize. I'm a little long-winded. Just trying to run this video out. So take care, everybody. Have a great day. Fill in those examples. And I will see you guys. Good luck. This is Mr. Fab saying, have a great day. Take care, everybody. Bye-bye.